Welcome to Calculus 1 class. Today we're going to review what we so-called the exponential and logarithmic functions. And now let us start with an exponential function. An exponential function is where our variable x is going to be on the exponents that has a base greater than 0 and not equal to 1. Because if my base is a 0, 0 to any power is still 0. If my base is 1, 1 to any power is still going to equal to 1. So we don't want our two bases to be those two numbers. And we will denote our exponential function as f of x equal to a to the x power, where a is our base, not equal to 0 and bigger than 1. Alright, so I can use any numerical number for my bases. Another choice for bases is this number called e. Alright, e is approximately 2.71828 something. It's an irrational number. We can also use that number as for a base. So that will be f of x equal to e to the x power. So e is just another number we use for the base. And here I have an example of the difference between using a base e versus using a base 2. Very similar. Okay. Very, not too much of a difference. It just base e is slightly bigger than base 2. All right. For this table, you're looking at the properties of exponents. Okay, we have anything to the 0 power is 1. So using 0 as exponent. Sorry about that. Using 0 as exponent, I can use 1 for exponent. Anything to the first power is the number itself. Product rule is where we will add the exponent. Quotient rule, subtract the exponent. Negative exponent rule is where we will flip it. Fraction exponent, okay, turn it into our radicals. And negative fraction exponents, where we will flip it again. And here are the three versions of the product rule, where we will multiply our exponents. Okay, so some of these you probably sing it in Algebra 1 and Algebra 2 class. Now, the inverse function, what is so-called the logarithmic function or log function, is the inverse function of an exponential. So that is to say that if I have an exponential function a to the x power, then its inverse, okay, will be log with the base a of x. That's how we read it. So what is a log function really? Is simply an inverse function of an exponential function. Okay, because an exponential function is a one-to-one function. So we can find its inverse, which is log with the base a of x. Now if I will change the base a numerical base, to a base e, then that becomes a natural log function. So what is a natural log? Natural log is simply a log function using the base e. Alright, so log is an inverse function of exponential. That's basically what log function really is. Alright, and here are the property of logs, and in a minute we're going to do some example where we will use the property of logs. A couple of things to keep in mind here. Right. Log with any base of 1 is always equal to 0. Same thing if I will change the base to an e, to have a natural log. Alright, log with the base a of a. Okay, if the base and what you're of are the same, okay, they will equal to 1. If the log of any base of a again, so the log of the base and what you're of, these two numbers are the same, in a way they kind of cancel each other out. So what I have left would just be the exponent. So that's why it's equal to x, and vice versa, of course. Alright, a lot of times that if we cannot figure out our answer from the logarithm perspective, we can actually change our log into exponential by simply move the base to the other side of the equal sign. And then we get x equal to a to the y power. Okay, that's a conversion between exponential and log equation. Change of logarithmic basis is where we cannot use a calculator to figure our logarithm, because on the calculator, this word log is actually used base 10. That's why the word log and 10 to the x power is right next to each other. They are inverse to each other. But when I type in the word log, that's actually referring to log with the base 10. Okay. So sometimes we will need to change our base to a different basis. Okay. And when we run into it, I will show you. Basically, this base A can be 10. This base A can be 10, or it can actually be E. So if I use a base E where the A is, that will actually turn into a natural log. Alright, logarithmic of products. If I have a log with a base A of n times n, I can split it up into addition of two logarithms. Log of quotient is where we will subtract. Logarithm of powers. Okay. If I have a log with a base A of some number to the x power, what we can do is move the exponent to the front of my log. Okay, that will be the logarithm of powers. Alright, base exponent property, we will use this property, and the property of logarithm equalities, we'll use these two when we're solving equations. So I will refer back to these when we run into it. So let's try some example. Okay, evaluate the following expressions. Okay, the trouble here is I cannot type in log with the base 2 because my calculator you only use base 10. So what I can do here is convert my logarithm into exponential. Look at it from the exponential perspective. So I'm going to use this property, convert between exponential equation and log equation. So I'm going to write my logarithm equal to this y first. Alright, all I'm going to do is to convert into exponential is bring my base 2 to the other side of the equal sign and put it below the y, and then what I get is 64 equal to 2 to the y power. Alright, so now I'm going to try to make the base the same, because if the base are the same, I can use the base exponent property. If the base are the same and the base are equal, I can set the exponent equal to each other and solve it from there. So to make 64 into a base 2, I believe 64 is 2 to the 6th power. 2 to the 6th power. Yep, 64 equal to 2 to the y power. So since my base are the same and base are equal, I can set the exponent equal to each other. So that means my y is equal to 6. Alright, so what that means is log with the base 2 of 64 is actually equal to 6. Okay, because where the y was is my answer. Now let's try part B. Alright, log with the base 2 of 1 over 8. Alright, same thing. I'm going to set my logarithm equal to the variable y. Move my base to the other side. I get 1 over 8 equal to 2 to the y power. Now my a is the denominator, so to make, we know a is the same as 2 to the 3rd power, because I want to make my base the same, equal to 2 to the y. So now the only trouble is one of my base 2 is on the numerator, the other one is denominator, so we will use the negative exponent property, which I will actually use it in reverse. Normally if my exponent is negative, we will flip the base to the other side of fraction and make my exponent positive. So now I'm going to look at it from in the reverse view. To my 2 to the third, if I will flip it back to the top, that will become 2 to the negative 3 power. So that will be 2 to the y power equal to 2 to the negative 3 power. So set my exponent equal, my answer y equal to negative 3. So this answer right here, log with the base 2 of 1/8 is actually negative 3. Okay. Alright, let's try part C. Log with the base 64 of 8. Alright, same idea. Log with the base 64 of 8. I'm going to set it equal to y. Bring my base 64 to the other side and put it below the y. And I get a equals 64 to the 8 to the y power. Excuse me. I know 8 times 8 is 64. So my 64 to the y power can be written as 8 squared for that 64. Whole thing raised into the y power. So here I can use my power rule and say this is the same thing as 8 to the 2y power, because I want to make the base the same. So that's 8 to the first power equal to 8 to the 2y power. So base are the same, base are equal. Set the exponent equal to each other. That means 2y equal to 1, y equal to a half. Alright, so my answer, log with the base 64/8 is actually a half. So a lot of times it's kind of difficult to understand logarithm. That's the reason why it's easier to convert our logarithm into exponential and look at it from an exponential point of view. Something that's easier to comprehend. Alright. Now the following example is expanding a logarithm expression and simplify. We want to I want to review expanding the logarithm here for a minute. And material like this got something to do with solving the logarithm equation. So remember the log of product. Multiplying means I can actually split them up into two terms with a plus sign. So for my part A, this is x to the third times square root of y. So that will give me log with a base A of x to the third. Multiplication means addition plus a log with a base A of square root of y. Alright. Now the log of power tells us that the exponent will need to go to the front. So that will give me 3 times log with a base A of x plus, and earlier we know that the fraction exponent turn into radical. So now I will do it in reverse. Square root of y is actually y to the half power, because the denominator of that fraction exponent determines the roots. The numerator 1 is telling that my variable y is to the first power here. So that's the reason why square root of y become y to the half power. And this half will need to go to the front of my log. So that would be half times log with a base A of y. Okay, and that's the simple. That will be in the simplest form here. All right. So for part B, let's take a look. The division means subtraction. Alright, so when I first write, so if I want to first write this thing out, it will be log with the base 4 of cube roots of xy minus subtraction division means subtraction, log with the base 4 of 64. Alright, and the cube roots will be the cube root of xy will be the xy to the 1/3 power. Right, because the denominator of that fraction exponent is the roots. The numerator tell me my x and y together in the inside the radical is to the first power. And this 1/3 got to go to the front of my logarithm, so that will give me 1/3 log with the base 4 of xy minus, alright, let's simplify this log base 4 is 64. Alright, another quick way to do this is by saying 64 is 4 to the 3rd power. Let me make sure. 4 to the 3rd power. Yep, 64. And earlier I said that when the base of the logarithm is the same as what we are of, they can kind of cancel each other out. So the only thing left will be your exponent. So that will just be minus 3 here. Alright. So that will be expanding the logarithm. Alright, now we're gonna do it in reverse, which is put them back to a single logarithm. Alright. So I see there's one subtraction here, so that means it gives me 2 terms, front and the back. Now the 2/3 is in front of that parenthesis, so that means this 2/3 belong to both of these logarithms. So technically what I have here is 2/3 log base 2 of x plus 2/3 log base 2 of y. Alright, and the plus sign will eventually becomes multiplication between the x and the y, and the 2/3 will hop back up on the 2 variable here. So basically what we have here really is a log with a base 2 of x to the 2/3 y to the 2/3. Since both of them is to the 2/3, I can say that's xy, the plus sign become multiplication of 2/3 power. Alright, minus means excuse me. Subtraction means division. I'm going to divide it by the x minus 4. Okay, so I can write it this way for my final answer, or I can write it as log with the base 2 of fraction exponent, turn them back into a radical. Denominator is the roots, so that will be a cube root of xy, whole thing squared. Or you can say x squared, y squared. No, still the same thing. Minus 4. Alright, so I can do it either way. Alright, write them as single logarithm. Now let me show you one example where I cannot make the base the same. Evaluate a log with the base 5 of 13. Now earlier, a problem like this one, I will write it equal to a y, move the base to the other side, and then trying to make the bases the same. But for this example, there's no way I can make base 5 and 13 into the same bases. So when we run into a problem like this, we're going to use another property. It's called the change of base property. Okay. So my log of 5 of 13, that will become log with the base a. The a can be a 10 or it can be an e of my 13 divided by log with the base 10 of my 5. So I'm going to write it down. Change your base. So the 5 is like the b, the 13 is like the m. So that will give me log of m, which is 13 over log of 5. And when I simply say just the word log, that means I'm using base 10. Or if I want to use base e, that will give me natural log of 13 over natural log of 5. And this is where it's bizarre. Log is using base 10, natural log is using base e. But if I would put it in the calculator, let's say log of 13 close parenthesis divided by log of 5. That's my answer. Round to 4 decimal place. Watch this. If I use the natural log of 13 divided by natural log of 5, give me the same answer, even though I'm using 2 different bases. That's kind of weird. Excuse me. 4 decimal place. That would be 1.5937. Alright, so in calculus you will see this base e from time to time, okay? Alright, let's turn our attention into solving exponential equation and logarithm equation. And let's do the exponential equation first. Okay, I'm pretty much going to use the same property as earlier. Just like this equation, this is an exponential equation. I'm going to try to make the base the same. Earlier I showed you that 64 can be written as 4 to the 3rd power. So this is 4 to the 2x minus 1 equals 4 to the 3rd. And when the base are the same and the base are equal, we can set the exponent equal to each other. So now this problem becomes 2x minus 1 equal to 3. And we will solve our linear equation. That would be 2x equal to 4, x equal to 2. Okay. There you go. So this variable x will end up to be 2. Alright, so the technique here is try to make the base the same. Alright, now what happens if the base cannot be the same while we're solving exponential equation? And there's something, well, what we can do here is actually take a logarithm on both sides. Take a logarithm on both sides. And here is the reason why I take a log on both sides. Because this property called the log of powers, when I have a log of powers, okay, if I actually take a log on both sides, the exponent will end up coming down to the front. And that's what and that's exactly what I wanted, is bring my variable x to the front. So now I will end up with x. If I take a log, this exponent come to the front, that will be x times log of 5, set equal to log of 17. Okay, that's the reason why I take a log. It's basically to bring the exponent down, okay, to the front, or bring it down. Now to get x by itself, I will just divide both sides by log of 5. Alright, so my answer, x equals around 4 decimal place again. So that would be log of 17 divided by a log of 5. 1.7604. Okay, that's all it is. Alright. Now normally when we see it, when we see e to the x power, okay, what go against e to the x power will be taking a natural log, because natural log and e, they kind of do cancel each other, just like what I showed you earlier. Okay, the log of base a of what you're of to, if they're the same, they kind of cancel each other out. Same thing with the natural log here on the right hand side. The natural log and e kind of cancel each other out, because technically what you got here is, for the natural log, is basically a log with the base e of e to the x. Oops, sorry. E to the x power. So the two e kind of cancel each other out. Okay, that's the idea. Alright, but that's what normally what most students will think to do, but not in this particular problem, because here I actually have 3 different terms here. Okay, so I can't simply just take a natural log, okay, and trying to get rid of all this e. Instead, we're going to use this technique. It's called the u substitution. I'm going to let my u equal to my e to the x. And here's the reason why. Because e to the 2x minus this 7e to the x, this equation is actually written in quadratic form. Alright, so think about this. If I'm going to let another variable represent my e to the x, what's going on with this first term, e to the 2x? Well, e to the 2x can be written as e to the x whole thing squared. And what I'm going to do is substitute the letter u for the e to the x. So that will actually give me what we so-called u squared. So this first term becomes u squared minus 7 times the e to the x becomes u now plus 6. So now this equation I'm solving is actually quadratic equation, because the original problem is actually in quadratic form. Okay, that's why I'm using the idea called this technique called the u substitution. Like another variable represents something in your equation. Alright, so if I will factor this quadratic equations, that'll be u and u. On 6, I will use 1 and 6. Both inner and outer are negative. So one of my u is 1. The other u is 6. But I'm not trying to solve for u in this problem. I'm trying to solve for x. So my u represents e to the x. So we will rewrite the u as e to the x equal to 1. E to the x equal to 6. So now I got 2 terms. If I only got 2 terms, I can actually take a natural log on both sides, because a natural log and e cancels out. So my x is equal to natural log of 1. Natural log of 1 is 0. So one of my answer is 0. Alright, the other answer, take a natural log on both sides. Alright, natural log and e cancels out. And the other answer is x equal to natural log of 6. And I think this problem says we're up to 4 decimal place. It'll be 1.7918. There you go. Voila. Those are my three answers. Alright, that's how we're solving exponential equations. Now let's take a look at how we solve logarithm equations. To solve logarithm equations, we actually want to, if we can, we want to make these two logs into a single logarithm. Okay, let me show you how the process, and let me show you why I want to make it into one logarithm. Subtraction sign here means division. So here, move the 2 back to the exponents. That means I should have a log with a base 3 of x plus 4 whole thing squared over 9 equal to 2. Alright, so why do I want to make a single logarithm? Because what I can do now is make the logarithm equation into an exponential equation by simply move the base to the other side. Now that would be x plus 4 whole thing squared over 9 equal to 3 squared. Alright, and 3 squared is 9, so I'm going to write 9 over here. Now I'm going to solve for x. So this 9 being 9 over 1, I can use a cross product to help me solve this. So x plus 4 whole thing squared times 1 is x plus, still going to be x plus 4 whole thing squared, equal to 9 times 9 is 81. So this quadratic equation only got 2 terms. So I can simply take a square root on both sides rather than expand the x plus 4 squared. Since I only got 2 terms, I'm going to take a square root on both sides. Because square and square root cancels out here. That will give me x plus 4 equals, and when I take a square root on both sides, my answer is always positive and negative 9. So subtract 4 on both sides. That'll be negative 4 minus 9, which is negative 13. Or the other answer, negative 4 plus 9, which is 5. So these are my 2 answers. Alright, now imagine if I will plug in the negative 13 back into the logarithm. Negative 13 plus 4 is negative 9. If I take a log of a negative number, it will always be not real answers. Okay, so we cannot take a log of a negative. So negative 13 cannot be my answer. Alright, so my answer would just be 5. So I turned the 2 logarithm back into a single logarithm because so I can make it into an exponential equation. Now another example, same thing. Here I got log for all 3 terms. Earlier I only got log for 2 terms rather than all 3 terms. So if I have a logarithm for all my terms, okay, my approach is going to be slightly different. Again, subtraction sign here tell me I will divide, so I will still make them into a single logarithm. So that'll be log of x plus 4 over 2 equal to, well, the other term here on the right side is also another logarithm term. Alright, so there's one more property I have not used, which is this last one here. Property of logarithmic equality. It's basically saying if you have 2 logs that are the same and they are equal, you can set what they are of equal to each other. Okay, you can set what they're of equal to each other. And that's what I got here. 2 logs that are the same base. Okay, so I'm going to set what they are of here equal to each other. So that means this equation is going to be x plus 4 over 2 set it equal to 5x plus 1 And I'm gonna use cross product again. Treat this as a 5x plus 1 over 1. So my x plus 4 times the 1 stays the same as x plus 4. So it equal to my 2 here in the denominator will times both terms on top. So that would be 10x plus 2. So move the x to the right, move the move the x to the right, move the positive 2 to the left. I should have 9x equal to 2. So my answer, x equal to 2 over 9. And that would be my answer here. Alrighty, so two different two logarithmic equations. The approach are slightly different, and the key difference is this problem has log for all 3 terms. The other one only got it for 2, or other than 3. So since the 2 here does not have a logarithm, I have to make my whole equation into an exponential equation before I can solve it. Alright, that will conclude this video. Thank you for